Greetings everyone, welcome back into Trig. Time to expand trigonometry into the world of the rest of all of the angles that are possible out there. Think about it. We've only defined trigonometry so far to work inside of right triangles, which is very limiting. Since I've already got a right angle in a right triangle, I'm limited to only acute angles for the other two angles. So can we only do trigonometry on angles that are in between 0 and 90 degrees? No. Trigonometry is much, much bigger than that. It's much more useful than that. Okay? We can expand trigonometry into the world of any angle possible, and it can still be based on the same definitions without having to change our ratio definitions. What we need to do is employ the standard angle that we've already talked about graphing on the XY coordinate plane and incorporating something called reference angles. So here's what we do. If you graph a standard angle, remember it comes off of the positive x-axis as the initial side, and then it rotates until it hits the terminal side. So if I'm in quadrant 1, my theta is an acute angle, which we already know how to do trigonometry for. Notice if I were to draw a right triangle including my angle here, it would look like this. I would put a dot here, and I'll just dash it since it's only kind of there, such that this is a right angle here. Notice the angle I've now graphed in standard position can also be thought of as inside a right triangle, and the opposite side over here happens to be the y value of this point. The x value happens to be the adjacent, right? Because to get to this point right here, I'd have to go x, then y. And what we do is we write down r for the hypotenuse. So let's say I have r right here, I've got x, and I've got y, like this. Well, okay, cool. That means all I have to do is define my sine, cosine, and tangent based off of the x, y, and r values that go along with this given angle, right? So basically, I've just picked some point on the terminal side, and it really doesn't matter which point you pick because it would be similar triangles. It's going to be the same angle, okay? So it would be a proportional size, and then therefore the ratios, the sine, cosine, tangent, are going to be the same no matter where you pick the point along that terminal side, okay? So the coordinates of this point right here are the x and the y that are being used for these lengths, and the r is the length right here. And of course, Pythagorean theorem, inserts itself here. R squared would have to be equal to x squared plus y squared for this to work. Next, I'm going to go ahead and write down the definition that we need from here. In quadrant 1, as you can see, I would basically be just defining the sine, cosine, and tangent using the x, y, and r values. Okay? So the sine of theta is going to be y divided by r. That's important to remember. The cosine of theta is going to be the adjacent over the hypotenuse. That's going to be x over r. And the tangent, I'll put it over here, is going to be opposite over adjacent. That's y divided by x. Okay? So in other words, if I've got an angle, I pick a point on the terminal side, and then that causes me to have a right triangle using the x and y values from the coordinates of that point. I can then create the r as needed using Pythagorean theorem, and I can define my trig functions, my trig operations, based off of just the coordinates of that point, right? So the angle is in there the angle is how you would define how we got from the x-axis up to that terminal side, but then the trig ratios come from the coordinates of that point. Okay, so Professor Simon, you haven't shown us anything new. Okay, we already know trigonometry is in right triangles, and that hasn't gone outside of the 0 to 90. You're correct. Quadrant 1 is still 0 to 90 degrees. Okay, but when I start rotating outside of that quadrant, quadrants 2, 3, or 4, right, I employ something called a reference angle. Now, a reference angle is exactly what it sounds like. It's an angle that I reference, an angle that I ask for some information. Okay? The reference angle is not actually my angle of interest unless you're in quadrant 1. Okay? If you're in quadrant 1, the angle is its own reference angle. Outside of quadrant 1, the angle is not equal to its reference angle. So it's literally just an angle that I'm saying, hey, let me ask you this information real quick. And then I get that information, and then I apply it to my given angle. Okay? The reference angle is something that's always a positive. It's always acute. Okay? And what that guarantees is that it will fit snugly inside of a right triangle. The reference angle should be something that fits in a right triangle. Now, one other important thing. It always connects the x-axis to the terminal side of your angle. Important. Read it again. X-axis to the terminal side. Never draw a reference angle to the y-axis. Our reference angles, by definition, must connect x-axis to terminal side. So here's what I mean. Notice quadrant 2 right here, right? Here's theta. It's rotated past 90 degrees, and it's going into quadrant 2. The reference angle for this is right here. The reference angle is the angle that's connecting the x-axis to the terminal side. The reason for this, it's very important. When I draw the right triangle, the reference angle is the angle inside of the triangle. So notice there's my right triangle here. I've picked a point on the terminal side. And once you pick the point on your terminal side, the point should always be connected to the x-axis. Now again, that's important, and here's why. Because when I define my trig ratios, I need the y value to be the opposite of the angle that I'm using to define the ratios. Why is that? Because I've already defined sine as y over r. If you try to use a reference angle up here instead, the opposite would be the x instead, and you'd have to switch up your definitions. Don't do that. Always do your reference angles to the x-axis so that my opposite side connects to the x-axis, and therefore y and x are preserved in the definitions that we've already listed here. These definitions should stay true at all times if you pick a point on your terminal side. Okay, so let's finish labeling these things. If this is y, the r, of course, is over here, right? The hypotenuse is r. But then look, the x is to the left now. Do you notice that this is negative x right here? Technically, it's still x. I would probably say it's the x coordinate, but I'm emphasizing the fact that this will be a negative number for a moment. I want you to notice that if you pick a point in quadrant 2, it will have a positive y component, but it will have a negative x component. Why does that matter? Well, you've defined cosine theta to be x, whatever it is, divided by r. Therefore, no matter what the angle is, if it's in quadrant 2, my actual cosine value will be negative. Here's a quick example to show you. Something that is in quadrant 2, 100 degrees, right? Make sure I'm in degree mode. If I hit cosine of 100 degrees, notice it comes out to be a negative number. Okay? That's important for you to notice. Depending on what quadrant you're in, different ratios will be positive or negative. And it depends on the points that you're allowed to pick on your terminal side. Okay? So notice in quadrant 2, anything related to x is going to carry a negative. So that means that in quadrant 2, sine theta is going to be positive. Cosine theta is going to be negative, and tangent theta is going to be negative. So notice only sine is positive in quadrant 2. Okay, what about quadrant 3? Well, again, where do we draw the reference angle? The reference angle has to be between the x-axis and the terminal side. So there's my reference angle right there. And then where's my right triangle going to be? I'm going to pick a point on the terminal side. I'm going to draw my y value up to the x-axis there. So notice now y is below the axis and must be negative. R is still positive and will always be. We've defined R to always be positive. Notice we're still to the left. X is still negative while we're in quadrant 3. So in quadrant 3, sine theta is negative because it'll be negative y over r. Cosine theta, still negative because it's negative x over r. But tangent theta is positive because you have negative y over negative x, and the negatives will reduce to a positive. So whenever you do tangent in quadrant 3, you'll end up with a positive value. Okay, so next, what about quadrant 4? In quadrant 4, I've rotated all the way around to here, and it's a little bit different for the reference angle, but it's the same idea. Now the reference angle is not connected, it's not part of the rotation anymore. Now it's the leftover rotation that's not being used to finish the cycle. See, over here it was finishing that. Here it was actually part of it, right? In quadrant 4, it's finishing all the way up to the x-axis. For the same reason, remember, we're connecting to the x-axis. So if I pick a point on the terminal side, like so, okay, so my y is negative, but now my x is positive because it's to the right now, and my r is always positive. So in quadrant 4, sine is negative. Cosine of theta is going to be positive, and tangent theta is going to be negative. Okay? Notice the cosine is positive here, and notice the tangent is positive here. Outside of quadrant 1, 2, 3, and 4, there's only one main trig ratio that's positive in each of those quadrants. Okay? And I have a little mnemonic to help you remember this in case you need to do it quick. I have the acts set up. A-C-T-S, acts, as in to act on something, or she acts on something, right? The acts set up. If you don't like acts, then there's another mnemonic that I've heard ever since high school, and it's all students take crap. Or all students take calculus. To a lesser degree, that could be true. But whatever, ASTC, notice that what these letters are standing for are what's positive in each of those quadrants. All trig functions are positive in quadrant 1. All. Sine is positive in quadrant 2. Tangent is positive in quadrant 3. And cosine is positive in quadrant 4. So if you just remember the axe setup, okay, then that will help remind you which of the trig ratios should be positive and which ones should be negative whenever you come across them. Okay, now again, we're still not limited to just the normal rotations in these quadrants. It just happens to be wherever your angle lands. And it can literally be any kind of angle. It can even be a negative angle. For a negative angle, remember I start on the positive x-axis and I just rotate in the clockwise direction instead, in the negative direction of rotation. But notice I still have to just pick a point and make a triangle, which means my reference angle would be here, as it's supposed to be for quadrant 2. So it's really not just about the angle. Remember, the whole point of trigonometry is relating the angle to a physical straight line length. And that's what we're doing here. I've related any angle that has this terminal side. It's not just this angle. Any angle that lands on this terminal side will have the certain y, x, and r combination. And any angle that lands on this same side will have the exact same sine, cosine, and tangent ratio values. It's not just about the angle. It's about where the angle lands, and that will directly give you the trigonometric ratios for that angle. And notice they will repeat. Once I've gone through quadrant 1, that's all of the possible sizes of right triangles, right? Quadrant 1 eats them all up. So once I get to quadrant 2, I'm gonna get some repeats. All of the right triangles that are drawn in quadrants 2, 3, 4, for negative angles, for whatever, any of those triangles, okay, are just repeats of the ratio numbers, but it will have different combinations of positive and negative, okay? So there's always going to be a repeating feature here to these. As your angle rotates around, it will go through several different repeats of the same sizes over and over again. By the way, you can also have angles of any size. I can have something that's bigger than a full rotation. Notice this one is 2 full rotations and then another obtuse rotation after. But the trigonometry remains the same. I pick a point on the terminal side, doesn't matter where, just somewhere on the terminal side, and I connect to the x-axis. My reference angle is going to be whatever acute angle fits in here. And then I'll be able to use my y, x, and r to accommodate the sine, cosine, and tangent ratios. Okay? Now, on the flip side, sometimes I can just use the reference angle to find the sine, cosine, and tangent ratios if I'm aware of what quadrant we're talking about. Okay? Sometimes you'll need to pick a point, and other times you'll just need to know the angle. Well, when do I need to just know the angle? We'll talk about the picking the point in a minute. Let's say it's one of the memorized angles that we talked about in the last lecture. For example, sine of 30 degrees. We already know this one. Notice 30 degrees is in quadrant 1, and sine of 30 is still going to be positive 1/2. That's just the way that one is set up. Well, what does that mean? One of the things it means is I could pick a point on here, right? I didn't have to because I already knew the sine of 30. But one of the things that I could have picked was the sine being 1/2, or I could have picked something like the point where this is 3 and this is 6, right? Either way, opposite over hypotenuse, 3/6 reduces to 1/2. There's all kinds of different things I could have picked, right? Any point along this terminal side would give me that same ratio. Okay, cosine of 225. Well, first thing I notice is that 225 is bigger than 180 degrees, but less than 270. So 180 degrees, of course, being this amount, right, a half circle, and 270 degrees being 2 or 3/4 of a rotation, right? So I know that 225 is somewhere in quadrant 3. All right. I need to know a reference angle if I can. Well, notice if I just draw my reference angle right here, it's got to be the amount of rotation between the terminal side and the x-axis. Well, I've gone past the x-axis. So this is 225 and this is 180. So my reference angle would have to be 225 degrees minus 180 degrees. The difference between the two sides there. Okay, so that means that my reference angle is 45 degrees. That's important to know. If it's 45 degrees, that's one of the memorized angles that we're supposed to know. I can do the cosine ratio of 45 degrees. We know that that's square root of 2 over 2. So the cosine of 225 is also square root of 2 over 2. But wait, we didn't consider one other thing. We're not in quadrant 1, and some things are positive and some things are negative once you leave quadrant 1. We are in quadrant 3, and according to our little anagram here, all students take crap, right? So I'm in quadrant 3, the tangent quadrant. That means only tangent should be positive from the 3 main ones. And I just did cosine, not tangent. So therefore this should be negative. Negative square root of 2 over 2. Okay? Now here, let's double check that real quick. First of all, the calculator's not going to give me square root of 2 over 2. Okay? These calculators are not designed to give you those kind of answers, and it's on purpose. We want you to be able to know that. So if I just hit cosine of 45 degrees, right? That's the one that you would normally see in quadrant 1 or just inside of a right triangle. The cosine of 45 is the 0.707. That's the decimal form of the square root of 2 over 2. Okay? So here I'm going to change the 45 to 225. And all you have to notice is that it's the exact same cosine value, the 0.707, but it's negative. So the cosine of 225 is exactly the same size as the 45-degree triangle, but because of the location, its values have negatives included in it because of the way the y and the x's are both negative for that region of the system. Okay, vice versa. The tangent of some angle is equal to the negative square root of 3. And theta, the angle, has been listed as something in quadrant 2. Well, let's make sure that makes sense first. Should tangent be negative in quadrant 2? Quadrant 2 is the sine quadrant, right? That means tangent should be negative. Yes. So far so good. Tangent theta is negative, and then the square root of 3. So I need to think to myself, I know of an angle that has a tangent ratio of square root of 3. That happens to be 60 degrees. Okay? So in the back of your mind or on your paper, whatever, because of this square root of 3, you should be saying, hey, my reference angle should be 60 degrees. Well, that means this right here is 60 degrees. So since this is 180 degrees, then theta is the other portion over here. I'm just going to do 180 degrees minus the 60 degree reference angle, and it's going to give me the other portion here. So 180 minus 60, theta is equal to 120 degrees. So if your angles are related to the three important special angles that I just talked about in the last lecture, then you can simply use reference angles and you'd be able to associate sine, cosine, and tangent values. Okay? If you go outside of the special angles and you don't have the memorized, ratios to go along with it, then you need to start picking points on the terminal side so that you can start relating the x and y values into sine and cosine and tangent ratios. Okay? Let's do a couple of examples related to picking a point or already knowing some trig information to the rest of the trigonometry that we've been talking about in the last few lectures. So, write the trig ratios associated with the point 5, -7 if 5, -7 were on the terminal side of your angle. Now remember, just because I drew theta this way, right, this normal standard positive angle theta to the terminal side containing the point 5, -7, just because I drew it that way here doesn't mean that that's the only angle that this would work for. Don't forget there's an infinite number of ways to land on this side. Okay? I could land going this way. I could land by going around one time and then ending up on that side. Whatever way you can imagine, as long as your angle lands on this side, then the 0.5 and -7 can dictate all of the ratios of whatever angle that is. I'm just using the theta the way it's drawn there just as a standard. Okay? So, once I know that the 0.5 -7 is on my terminal side, I can imagine drawing a right triangle using the reference angle in here, right? This would be my reference angle here. And then the -7 is going to be this y value. The 5 is going to be the x value. And I need to know an r value. So I'm going to solve for r. R squared is going to be 5 squared plus -7 squared. So r squared is 25 plus 49, which tells me r squared is equal to 74, which I then take the square root. And remember, we said this, the r is always positive, so I'm not going to put plus and minus here for the purposes of basic trigonometry. Our r is always positive. Now later on, when you get to more advanced systems and trying to do different coordinate systems, they'll define a different, more general r that can be both positive and negative. That's not what we're talking about. This is just your basic definition of basic trigonometry on the plane. Okay? So r is going to be the square root of 74. Let's see, which is what, 2 times 37. So yeah, you're not going to go anywhere with that one. Just leave it as square root of 74. So that's my r side over here. I'm going to put square root of 74 for that side. Here's my right triangle. So now I can just set up my trig ratios. Now remember, it doesn't mean anything to just write SIN. I have to be applying it to some angle because that's the relationship. The sine of the rotation is then equal to the ratio of -7 over square root of 74, which of course we're going to want to rationalize. So that'll be -7 square root of 74 over 74. Okay? Cosine theta is going to be 5 over square root of 74, which is rationalized as 5 square root of 74 over 74. Tangent of theta is going to be y over x, negative 7/5. Okay, so let's do the lesser three, right? The cosecant of theta is the reciprocal of sine. So I'm just going to flip this guy right here. And that's going to give me negative square root of 74 over 7. Secant of theta, reciprocal here. So square root of 74 over 5. And cotangent of theta is going to be negative 5/7, reciprocal of that one. Okay, so I have my 6 trig ratios associated with any angle that hits the terminal side containing the 0.5, negative 7. All right? Now, something that we've seen a little bit before, but just a more generic version of, if I give you one of the trig values, one of the trig ratios of some angle, then you should be able to find the other 5 just from that information. And I'll also, you need to know one other piece of information, and that is which quadrant it's in. Because that's important, right? Knowing which quadrant you're in is going to change whether something is positive or negative in your ratios. Okay, so here I'm in quadrant 3. Remember, we have our little mnemonic, all students take crep. I'm in the tangent quadrant, which means tangent is positive. Also notice cotangent is positive. Cotangent is positive as well. So I'm going to start, I'm going to work it 2 different ways. I'm going to start with the, what I called the ACT method last time, remember? And that is, if I know where my angle is, my reference angle is here, my triangle is here, right? Then I can label the triangle using the information given. Now, cotangent is the reciprocal of tangent. And remember, tangent was defined as y over x. So that means cotangent of phi must be x over y. Therefore, a point on my terminal side must be the point negative 11, negative 8. Wait a minute. Where'd those negatives come from? Hang on a second. There's no negatives up there, right? Have a little spatial sense, right? I'm in the 3rd quadrant. My x is to the left, my y is down. They both have to be negative. It's just that the division of 2 negatives gave me a positive here. So I know that since this is x over y, it should technically be negative 11 over negative 8. Right? Okay. So therefore I can label my triangle using that information. Negative 8 is the y. And negative 11 is the x. I can then find an r value. R squared is equal to negative 8 squared plus negative 11 squared. So r squared is equal to 64 plus 121. R squared is going to be equal to 185. And let's see, 185 adds up to 14, so it's not divisible by any of those. So r is just going to be square root of 185. Okay. And then that means I can label this over here, square root of 185. Right? Let's see, 5 into 185. Let's try and reduce that one if we can. It's 3 shy of 40. So what, 37? Yeah, because 150 and 35. Yep. So that can't be reduced any. This is that's as low as that one's going to go to. Okay, which means just like before, if I know all 3 of the sides in my triangle, I can set up any of the trig ratios from this. I can do sine, I can do cosine, I can do tangent of phi. So that's one way to do this. One way to get all of those is to fill out your triangle and then just start writing the information from the diagram. Okay? Let's incorporate those identities from last time so that you can also see that they still work even in this generic system. I have the cotangent of phi as 11/8. Reciprocal identity says that tangent and cotangent are reciprocals. So the tangent of phi must be 8/11. That's a reciprocal identity. Okay. Between these two, I'm going to choose to use the tangent, and I'm going to use a Pythagorean identity. The Pythagorean identity I'm going to choose is the tangent squared of phi plus 1 is going to be equal to secant squared of phi. Okay? So from this, right here, from this, I'm going to plug in the 8/11. It's squared because of the tangent squared, plus 1 equals secant squared phi. I want to simplify this side, so I have 64/121 plus 121 over 121, because I'm squaring here, and I'm writing 1 as 121 over itself so that I can have a common denominator. And then that's going to simplify to 185 over 121, and that's still equal to secant squared of phi. So here, if I square root both sides, right? If I square root both sides, then I've got the square root of 185 over 121 plus or minus is equal to secant of phi. Okay, now in the last lecture video, right, when we were talking about these identities, I just assumed positive all the time because we were only dealing with right triangles. Now that we're in the broad system, you have to remember, well, wait, it could have been negative or it could have been positive. So this right here, this is the choice that's going to set up the rest of your information to be correct or incorrect. Okay? I'm going to reference back up to my information, and I'm going to notice, hey, phi is in quadrant 3. So that means tangent is positive only, well, with cotangent. So then all of the other 4 must be negative. So I'm going to choose the negative here. I'm going to choose negative, and it's going to be square root of 185. I can do the square root of the 121. It's just going to be over 11 equals this secant of phi. So now I've got secant, which of course from a reciprocal identity means I also automatically have cosine. So cosine of phi is going to be the reciprocal of this, negative 11 over square root 185. Of course, I'm going to want to rationalize that. Negative 11 square root 185 over 185. Okay, so now I've got cosine. And then to finish this up, I'm going to make a little bit of space here. To finish this up, I'm going to use the quotient identity. The quotient identity that I'm going to use is the fact that tangent of theta is equal to sine theta divided by cosine theta. Right? I picked that one on purpose because it's very easy to get the sine theta isolated there. Watch. Since this is an identity, I'm actually allowed to manipulate it algebraically. I can actually multiply both sides by cosine theta like this, so that this will reduce. And notice what I have is that sine theta is equal to tangent theta times cosine theta. which is 100% another version of that same identity. Okay, so I'm just going to separate this here. Cosine theta, I already know. I'm going to use this guy right here. That's negative 11 square root 185 over 185 times tangent theta. Oh, you know what? All of these should be phis. I apologize. I just caught myself. I hope you caught me earlier. All of these should be the angle phi. Sorry about that. Now it's correct. Cosine of phi is this measurement. Tangent of phi is 8 over 11. And it's equal to sine phi. Notice 11 over 11 will reduce, and I'm left with negative 8 square root 185 over 185, which is going to give me sine of phi, which is what I was looking for. And I need cosecant phi. Okay? Compare the patterns here real quick. Do you notice how when I went from secant to cosine, I had to rationalize? So imagine this sine phi right here is not rationalized. It would just be a square root of 185 and an 8. And I just need to reciprocate that. I need to flip that. So this is just going to be negative square root of 185 over 8. Okay? So I can use the identities to find any of the trig values as long as I know one of the trig values and which quadrant we're talking about. Okay, you have to have those two pieces of information in order to fill out the rest. Also note that you could have done it this way by filling out a triangle and feeding, this should be a right triangle, feeding from the right triangle. And it really is going to depend on how much efficiency and speed you want, or if the directions physically might ask you to use the identities to do this. There are a lot of problems out there just for practicing the identities where they want you to do it this way so that you can build up your skill algebraically manipulating these trig functions. Okay? All right. I also need to add 4 more special angles for you to remember, and it's just as important that you know these as those first 3 that we talked about in the last lecture. These are special angles because they're not in any particular quadrant. We call these the quadrantals, and they are the angles that you rotate to hit one of the axes sides. Okay, so we have 0 degrees, 90 degrees, 180 degrees, and 270 degrees. And I'm going to start shifting over to radians the further we go along here, because that tends to be the system that we like to use when associating trigonometry to the actual physical world. Okay, and I'll be doing a lot of both, and then in later triangle applications we'll switch back to degrees again. Okay, so here what you need to remember is just our definition of sine, cosine, and tangent using points that are on the terminal sides of these angles, right? So let's write those down real quick. The sine, cosine, and tangent were defined. The sine of some angle is y over r. The cosine of some angle is x over r. And the tangent is y over x. Right? So we'll be using those 3 definitions to say these. And what I really need to do in each of these situations is just pick a point on the terminal side of the angle. Okay? So for 0 degrees, there's no rotation. There is 0 amount of rotation. So the terminal side is the initial side right here on the positive x-axis. And I could really pick any point on there okay? But I'll choose the point 1, 0. The point 1, 0 is on that terminal side. So the sine of 0, and notice I'm not using degrees here. I wrote degrees here, but I'm going to start using the radians. So sine of 0 is still 0 radians, is equal to the y divided by the r. Now watch, the r in this case is also on top of this. The x value is 1, but so is the r, okay? So sine of 0 is actually 0 over 1, which is 0. The cosine of 0 is 1 over 1. The x value over the r value, 1 over 1, which is 1. And the tangent of 0 is, again, y over x, which is 0 over 1, which is going to be 0. Okay? For me, I'm going to show you this little diagram. When I was in high school, for some reason, I just wrote this down and the diagram just always stuck to me. I remember thinking on this side of the axis there was a 0, 1, 0. So for 0 angle, right, the sine, cosine, tangent was 0, 1, 0. And I'm going to fill out that mnemonic as we go. Okay, 90 degrees. I'm going to pick the point on the terminal side here to be 0, 1. Okay, that means that also my r value right here is 1. My r value is also 1. So the sine of pi over 2, which is the sine of 90 degrees also, is equal to 1. Because that's y over r, 1 over 1. The cosine of pi over 2 is then equal to 0, because it would be x over r, 0 over 1. And here's a real kicker for you. The tangent of pi over 2, the tangent of 90 degrees, is undefined. Okay? Because it's y divided by x. 1 divided by 0. It's a division by 0. There is no number for that answer. So your tangent of 90 degrees, your tangent of pi over 2 radians, is undefined. Okay, on to 180. You'll notice that for 180 degrees, it's going to be pretty much a repeat of 0. And that's because they're on the same axis. However, one minor difference. When I pick the point on the negative side of the x-axis, I'm going to pick something like negative 1, 0. So the only thing that's going to change is the SIGN of the cosine. So the sine of pi, 180 degrees, is 0. The cosine of pi, 180 degrees, is negative 1. And the tangent of pi radians is again 0. 270, you'll find, again, there's a repeat. And you're going to see that a lot in trigonometry. There's a lot of repetitive natures in trigonometry, hence the whole sinusoid that we study later. The point that I'll pick is on the negative y-axis. That'll be 0, negative 1. Okay, so then the sine of 3 pi over 2 radians is negative 1, right? Same pattern here, but it's just in the negative direction. The cosine of 3 pi over 2 is then equal to 0. And the tangent of 3 pi over 2 is undefined. Because yet again, you have a division by 0. Y divided by x is negative 1 divided by 0. So you get your undefined tangent value there. Okay, so here, let me finish filling out this mnemonic for you. whenever I was in high school, like I said, that for some reason I just always saw these things. 1, 0, undefined. 0, -1, 0. -1, 0, undefined. And for some reason, this always stuck out in my head. Like I could just picture it. And it would help me remember the sine, cosine, and tangent of each one, right? So for 90 degrees, sine, cosine, tangent, 1, 0, undefined. Now, let me be clear. The circle with a slash through it like that is technically not necessarily the undefined symbol. It's overused and misused that, but it's good for a visual. And like I said, this is what stuck in my head back when I was young. You know, Stone Ages, a long time ago. Okay? And I want to show you a chart here. Okay? This is a complete chart of all 7 special angles. These are the 4 new ones and then the 3 from last time. First thing I want to show you is that there's a pattern here. Okay? If you can build the sine pattern first, everything else sort of just comes out of that. Okay? So watch this. You can count 0, 1, 2, 3, and 4 for these. Okay? Now here's what happens. What you want to do is you want to square root each of these and then divide by 2. So square root, divide by 2. 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 But you notice how they count, right? Some of these can be simplified though. Square root of 0 is 0. Anything 0 divided by anything is 0. So this cancels out and you just get 0. The sine of 0 is 0. True. The square root of 1 is 1. So I just get 1/2. Sine of 30 degrees, pi over 6 radians, is 1/2. That's true. Square root of 2 over 2, already simplified. Square root of 3 over 2, already simplified. Square root of 4 is 2. And 2 over 2 is 1. And notice the sine of pi over 2 is 1. So if that helps you in any sort of way, then you can build your memorized values this way. By counting, and then you do the square root and then divide by 2. Then you just have to remember that pi mimics the 0 angle, right? So I'll have 0, and the 3 pi over 2 mimics the pi over 2 because they have the same denominator, right? So -1. A lot of times you'll find when those denominators and radians are the same that they have a lot of the same patterns. Okay, now any cofunction pairs, remember the complementary pairs, are going to swap sines and cosines. Here's your center right here. Pi over 4 is your center. The sine and cosine are the same. And then as you go outward from that, they crisscross. So I go out 1 on either side. These 2 are going to switch. So this will be square root of 3 over 2. This one will be 1/2. And here, this is 1 and this is 0. They will also switch. Here's 1 and here's 0. Then you just have to remember that the 0 and the pi have the same pattern. So -1 and 0. See, these are switching also. And then to get tangent, you simply do the sine divided by the cosine. So 0 divided by 1 is 0. 1/2 divided by square root of 3 over 2 is going to give me 1 over square root of 3, or square root of 3 over 3. Something over itself is 1. Square root of 3 over 2 divided by 1/2 is the square root of 3 over 1. So just square root of 3. 1 divided by 0 is undefined. And then you have the same thing here and here as the other two. Okay? So that's a chart of all of your angles in radian measure and their sine, cosine, and tangent that you are supposed to know the exact value, not necessarily the decimal value Okay? These are the things that you're always going to be expected to just know whenever you're doing sines and cosines and tangents. Those are the special angles. Another quick addition to our repertoire here is another family of identities, and that's the even and odd identities. And these are real quick little algebraic consequences of the way we've expanded into the larger angular system. Sine is an odd function. By odd function, I mean the algebraic definition of any function where if you plug in the opposite of an input, you get the opposite of the original output. That's the definition of an odd function. Something like cube, right? 2 cubed is 8, but negative 2 cubed is negative 8, right? So x cubed is an odd function because of things like that. Sine is an odd function for the same reason. If I plug in a positive angle, theta, I'll get y over r. And if I take the same size angle and go in the negative direction, I'll get the same size y, but in the negative over r. So I will get the actual opposite sine value, right? It'll be negative y over r. And it doesn't matter if it's between these two quadrants or if I actually rotate to the second quadrant, the negative will rotate to the third. I'll have a positive sign and a negative sign. And it doesn't stop there. Okay, this doesn't guarantee that when I plug in the sine of theta, I'm going to get a positive, and the sine of negative theta will always give me a negative. No, no, no. What it means is if you pick any angle, theta, do the sine of it, and then do the sine of the negative of it, those two things will be opposite in SIGN sign. One will be positive, one will be negative. Okay, there's no guarantee of which one is which. Okay, so quick here. Here's a couple of quick examples for you. The sine of 30, we already know that one, right? That's a half, 0.5. What if I do sine of negative 30? Notice it's negative 0.5. Okay, or for example, what if I did sine of 200? That's something in quadrant 3, right? So the answer is negative. If I do the sine of negative 200, notice it's the same numbers, but positive. Okay? That's what it means for the sine to be an odd function. If you take any input and change it from positive to negative or negative to positive, either way, if you change the SIGN, then the answer will also change SIGN. Okay? Now cosine, on the other hand, is even function. Cosine's an even function because cosine is based off of the x value. All right? So if I rotate up or if I rotate down, as long as they're the same size, they will be sharing that adjacent side. And it doesn't matter if I rotate way over here as well. They're always going to share that x value, which means whether your rotation is negative or positive, you will always get the exact same thing. That's what even functions do. The algebraic definition of an even function is any function that takes a negative input and returns the same answer as if you had given a positive input. Something like absolute value or square. Those things tend to get rid of negatives. Cosine is the same way. If you plug in the opposite of an input, it actually does not change the answer at all. Okay? So here's a couple of quick examples for you. Cosine of 100 is the negative 0.1736. And if I do the cosine of negative 100, notice it's the exact same thing, negative 0.1736. Okay? Cosine is an even function. Now everything else, I can use the old identities to base off of sine and cosine. Okay? Tangent is odd because tangent is sine divided by cosine. You have an odd divided by an even, you're going to get an odd. Cosecant and cotangent are the reciprocals of those two, so they're going to have the same feature. And then since secant is the reciprocal of cosine, then it's going to have the same feature of being even. Okay? So in any of these instances, if you run into a trig function when you need to switch the SIGN of your input, you can automatically expect what kind of output it's going to have. Also, this gives us a way of simplifying some other algebraic run-ins that we'll have whenever we have negatives flying around in places and you might want to make one appear or absorb one or whatever. Okay, so this is another set of identities that helps us whenever we're trying to either solve or simplify these expressions. Let's finalize this connection that we have between angles and physical measurement. I'm going to talk about the unit circle now. And sometimes when you hear somebody say, hey, we're doing the unit circle, they don't necessarily mean the whole thing that I'm talking about here. They mean one small little part of it that we will discuss. Okay, when somebody memorizes the unit circle. I'm being more generic than that. A unit circle is any circle that has the center at the origin and a radius of 1. So this circle that I have here is a unit circle because I'm defining its center at 0, 0, and I'm giving it a radius of length 1. All right, so as you can see, just like before, I can pick a point on the terminal side of an angle. But the extra caveat that I'm throwing in here is the point that I'm picking is physically on the unit circle. So what that guarantees is that my R is going to be 1. So if I have an angle, and I'm calling it T here now, the radius from the center out to the circle is a distance of 1. And that's going to count as my R here. If I were to draw my triangle for this guy, right, it would be here, be the right triangle here. So then, of course, this would be my Y, and in this case, the X is negative, but I'll just put Y and X. And you'll notice the R is 1. So I have the same connections as before, the same definitions, except I can do one slight simplification. If I'm on this circle here where the R is 1, sine of angle T is going to be Y over R, which is Y over 1, which is just Y. And cosine of T is going to be X over 1, which is just X. So what does that mean? It means if I pick a point on the unit circle, okay, whatever angle it takes to rotate out to that terminal line that intersects with that point, the coordinates of the point will be cosine T, comma, sine T. Okay? So if you have a point on the unit circle, specifically on the unit circle now, okay, then the coordinates of that point are going to be some combination of a cosine and a sine of the angle, specifically the angle that it takes to rotate out to the line that intersects that point on the unit circle. Now let's expand it one more level here. Remember, we talked about arc length in the very first lecture. The arc length is going to be the length of the piece of the circle from the beginning of the rotation to the end of the rotation. So from the initial side to the terminal side there. So we're talking about this arc right here from the point on the x-axis, which is the point 1, 0, by the way. So if I walk on the unit circle, from 1, 0 out to some point xy that's on the unit circle, the length that I'll be walking is the radius times the angle, as long as the angle is in radians. So I'm saying right here, T is an angle measurement in radians. So the length of this is going to be 1 times t, because it's radius times angle, which is also t. So get this. Not only is t representing the amount of rotation now, since it's on a unit circle, t also represents a physical length from a starting point to an ending point on this circle. So if you were actually moving a physical distance from some point all the way out to this point here, okay, from not just some point, but 1, 0 actually, all the way out to some point over here on the same circle, that physical measurement of t distance then also gives me the coordinates of the point I'm landing on. That is a direct connection of rotation to physical length. This rotation gives me this length, which actually gives me the coordinates of where I am on that particular shape. So we can now actually, whenever we use radians, that is an actual physical connection that cosine and sine represent an x value and a y value on the grid somewhere on your coordinates. And that allows me to generalize these not just to calculations, but to full-blown functions. These things are actual functions of some distance now. And you can calculate the answer being the x or the y position. So I can actually say x equals cosine t, and that's some function that I have now connected and can analyze. And that's what we'll be doing in the coming lectures. We'll be talking about using the sine and the cosine and the other ones as actual functions of some radian measurement t, which is actually now, as you can see, some physical measurement of an arc t. Okay, now to get more specific, whenever someone says, I know the unit circle, I've memorized the unit circle, it's exactly what I've already recommended that you should start memorizing as far as special angles go. We've already talked about the 0, 30, 45, 60, 90 degree ratios, sine, cosine, and tangent of all of those special angles. Okay, so the way we've generalized this into all of the different quadrants, you actually have those same special angles in all 4 quadrants. Okay, so I've got the 30 degree angle, but let's say I want to apply it to quadrant 2. The physical angle right here is 30 degrees right here. Okay, this angle right here is 30 degrees. But notice it's actually labeled 150 degrees on this line because that's the angle from standard position. But it has a reference angle of 30 degrees. All right, so the sine, cosine, and tangent of 5 pi over 6 is going to be the same size, the same number parts as the sine, cosine, and tangent of 30 degrees of pi over 6. Okay, so right here, I can actually say that I know the coordinates of this point. Right here, I can say that the coordinates of that is the cosine of 150 degrees, comma, sine of 150 degrees. And I know that the cosine of 150 and the sine of 150 are going to be the same numbers as the cosine and sine of 30 degrees. Why? Because it has 30 degree reference angle. But it's in quadrant 2. So the cosine is negative and the sine is positive. Remember, all students take crap, right? So in quadrant 2, sine is positive, but cosine is negative. So the cosine of 30 is square root of 3 over 2, but cosine of 150 will be negative square root of 3 over 2. Sine of 150 will be sine of 30, which is 1/2, and sine of 150 is also positive 1/2. So this is the actual coordinates of this point on the unit circle. Notice I didn't have to memorize all of these different angles. if you remember these three angles, and you also know what has to be positive and what has to be negative in each of the quadrants, then that's all you need. And you can build the rest of these. Here's another example I've already drawn out. 4 pi over 3 has a reference angle of pi over 3. Notice the connection. Everything that has an over 3, over 3, over 3, over 3, all of those have the same reference angle. Those all have a reference angle of 60 degrees, which is pi over 3. Okay? 4 pi over 3 is just 4 times pi over 3. 4 times 60, 240. See, it's easy to convert these if you think of them as multiples like that, right? 5 pi over 3. 5 times 60 is 300. Pi over 6 is 30 degrees. 11 times 30 is 330. Okay? So if I know these three, sine, cosine, and tangent, then I know all of these sine, cosine, and tangents, and I just have to make sure and use the proper positive and negative values. Okay? So for example, the cosine of 4 pi over 3. I'm going to look at the cosine of pi over 3 because that's his reference angle. Okay? It would be 60-degree reference angle from the x-axis, which right here at 180, it would be a 60-degree angle or a pi over 3 angle from here to here. Okay, 60 degrees or pi over 3 is the reference angle for 4 pi over 3 or 240. Okay? So, the cosine of pi over 3 is 1/2. But quadrant 3, cosine is negative, so I have negative 1/2. Okay? Sine of 4 pi over 3 is the same thing as the sine of 60, sine of pi over 3, which is square root of 3 over 2. But quadrant 3, sine is negative, so it's negative square root of 3 over 2. And that would also correspond to the coordinates of that point on the unit circle. Okay? So, go back and look at all of the three main angles that you remember. Look at the sines, cosines, and tangents of those. Okay? And use them to find the sine, cosine, and tangent of all of the rest of these quadrants and all of their angles that correspond to them. Okay? The ones with the over 6s have the 30-degree reference angle. The ones with the over 4s have the 45-degree reference angle, so on and so on. All right? Let's finish up this series of scenes, finish up this lecture with a few examples pertaining to that unit circle theory that we were just discussing. Okay, so here, what are the coordinates for theta is equal to 7 pi over 4 if I'm on the unit circle? So in other words, if I were to rotate 7 pi over 4 radians and we're actually physically on the unit circle, right? I know it looks more like a unit oval. My drawing is not good for hand. But the coordinates of this point at this amount of rotation. All right, so what I have to remember is that all of the things with the over 4 are going to have that reference angle of pi over 4. And notice that that's actually true. If you were to subtract this out, this would be 2 pi, right? That's a full rotation, minus 7 pi over 4 gives me pi over 4, which remember is 45 degrees. Okay? And if I'm on the unit circle, the x is just the cosine and the y is just the sine. So I've got cosine 7 pi over 4, comma, sine 7 pi over 4. I'm going to use the reference angle to get the number portions of the answers. The cosine of 45 degrees is square root of 2 over 2. The sine of 45 degrees is also square root of 2 over 2. And in quadrant 4, cosine is positive And in quadrant 4, sine is negative. So here are the coordinates of that point on the unit circle. Next, if I have a point on the unit circle that has an x-coordinate of negative 3/8, find the y-coordinate if we know that theta is the angle in quadrant 2. Okay, so again, we're on the unit circle here, right? Radius 1, centered at the origin. And I know one of the coordinates, but not the other. And I know that it's in quadrant 2. Okay, well remember, the coordinates here tell me that the cosine of my angle theta, right? Theta's right here. The cosine of that angle is going to be negative 3/8. Because I'm on the unit circle, the cosine is just the x-coordinate. So from here, what I'm going to do is compute the sine using my Pythagorean identity, right? Sine squared theta plus cosine squared theta is equal to 1. And I just found out that cosine theta is negative 3/8 squared in this case because of the identity. All right, so that means that sine squared theta plus 9/64 after I square it, right, is equal to 64/64 because I'm writing 1 with a common denominator there. I'm going to subtract the 9/64 from both sides. And that's going to tell me that sine squared theta is equal to 64 minus the 9 here is going to give me 55/64. And then I'm going to square root both sides. So sine theta is going to be equal to the square root of 55/8. And should I pick positive or negative? Well, let's look. In quadrant 2, sine theta is positive. So I'm going to leave it just like this. This is my sine theta. And if you remember the definition, y is equal to sine theta. So my y coordinate right here is equal to the square root of 55/8. That's the y coordinate for that point. All right. What angle is associated with the point on the unit circle that has coordinates 1/2 and negative square root of 3/2? Okay, so I've got the unit circle here, maybe, if I can draw it good. The unit circle there, and I'm noticing that my x is positive and my y is negative. Okay, so if my x is positive and my y is negative, then I'm going to be somewhere in this quadrant of quadrant 4 here. Okay? So then my radius will be here, and it's 1 because it said the unit circle. And I'm looking for this angle here. It always helps to draw these things out in trigonometry, especially when you're just getting used to how to set these things up. Okay, so the first thing that I see is that I have a cosine, because these are the coordinates, right? On the unit circle, the x is always the cosine theta, and the y is always the sine theta, right? Well, since the cosine is 1/2 and the sine is square root of 3/2, that's one of those memorized angles. You got to think about it for a second. Which angle has a cosine, right? Cosine of what is 1/2, where the same question is the sine of what is square root of 3/2. And notice I'm just focusing on the positives here. The negative just helped me locate the quadrant. What I'm doing is I'm locating a reference angle, right? So size-wise, which angle has a sine of square root of 3/2 and a cosine of 1/2? Well, that's 60 degrees. 60 degrees has that sine and that cosine, which we're going to be using the radians pi/3. Now remember, that's not my angle. That's just coming from the sizes. To get the appropriate positive and negative in quadrant, I'm going to use that angle as a reference angle. I'm drawing it from the x-axis to my terminal side. Well, okay. I'm interested in this angle though, this angle right here. So if this is 2 pi, then my angle over here would have to be 2 pi with the reference angle taken away from it. Okay? So my angle theta is going to be 2 pi minus pi over 3. 360 minus 60 basically. Okay? But I can do this by saying 6 pi over 3 minus pi over 3. Just to get a common denominator there, I multiplied by 3 on that one. Which tells me that theta is going to be 5 pi over 3. Or in other words, 300 degrees. So it's important that you know those memorized angles also so that we can go in reverse without the assistance of a calculator. I hope this section has helped you broaden your trigonometry horizon here into the bigger world that trigonometry is applied to all angles and all aspects, and how I can also associate it with actual coordinates in a plane.